that makes sense.
Good. Very good. Um, yeah, so there's sort of one problem for us left, right? And this one's a little bit tougher.
I don't really see how this one correlates to the other problem though necessarily.
You're talking about this kind of like, what the heck do you call this object? It kind of looks like one of those like Jello cups that you maybe ate when you were 6 years old, right? I don't know, or at least I think I had them. But what do you want to call these? Jello cups, like demented circular trapezoids? What are these? Um, okay, Jello cup integration.
Jello cup
I
integration.
don't know. I've never heard of anyone actually come up with a name for these, so maybe I'm coining it now. But okay, so the idea here is you said that you don't quite see how this correlates with what we had earlier. And I'd like us just to visit that statement a little bit, right? Because what we were doing earlier was a lot of uh, integrating tiny little cylinders, right? Tiny little disks. And just visually, I can very much visualize just doing an infinitesimal disk at an arbitrary layer of this thing. Can you agree with that statement? Right? I can
Yeah.
imagine doing like an infinitesimal cylinder. So, at least at first glance, I would say that it definitely is related. But the hard thing for this problem is figuring out a good relationship between area of the circle, area of the base of the cylinder. Finding we so we what we need to do is WTF means want to find. So relationship, which kind of means a function, between the area of uh, the differential cylinder, or I'll call it the of the disk maybe, and our integration variable. What should our integration variable be? If I draw this coordinate system as, I don't know, this is 0, 0, and this is x, and this is y, would you want to integrate with respect to x or y?
Looks like let's see.
Yeah. Okay.
I'm starting to understand it more.
That's good. That's good. So we decided after this long conversation that we're integrating with respect to dy, right? Where relationship between area of disk and integration variable, which we decided is y. So now we're unfortunately coming across I'd say a slightly difficult problem. And it's not even a calculus problem. It's almost like an algebra problem. It's just when you see problems, even if you know how to do them in isolation, the fact that they're buried inside a calculus problem can sometimes seem really intimidating. But area, remember, area is just pi r squared, right? They've already called dibs on little r and big R. So I need a sort of variable length r. Um, gosh, I'm out of ideas here. God, the hardest thing to do is choose a symbol. I'm going to choose a symbol, sigma, just for no good reason, right? And sigma is a variable associated with sigma is basically going to be the length of the radius for
Okay.
for a given height. For a given height that specifies the typical disk, and for that typical disk, I'm going to call sigma to be the radius.
Okay.
Yeah. And the trouble here is that we need to come up with a relationship between y and sigma. Or like more specifically, we need to express sigma as a function of y. You see what I mean? Because I'm just going to write things out again. Sorry. Want to find sigma as function of y. And if we can get this, we're done. Because just to remind you from before, we're
Can I
integrating.
take a guess?
What's up? You
Can
want
I
to take a
take a
guess?
guess?
Well, go for it. I don't actually know what the correct answer is off the top of my head because I haven't done it myself, but go for it.
Would wouldn't it just be pi sigma squared?
Well, that's right. That's right. I was just about to get to that. But that's correct, but it doesn't give us enough information to solve it because this is a times dy, right? And this is just pi sigma squared dy. But the reason we can't just leave it here is because I don't actually know I don't have any information about sigma yet. Right now, it's just a name. I need to express this as a function of y. And then once I can actually express it as a function of y and square that, I can integrate that with respect to dy, and then we're done. You see that? So this entire problem
Yeah.
boils down to whether I can express sigma as a function of y.
Okay.
Gotcha. I'm going to draw a new diagram just because that one's getting kind of cluttered, right? But this time around, I think I'm just going to draw it as like a 2D diagram. Like a 2D cross-section looking from the side, so it looks like a trapezoid, I think.
Okay.
Yeah? Can you buy this? So then this height up here is still little r. And this height down here is big R. And at an arbitrary point in between, this height is y. And I really want to find an expression for sigma in terms of y. If we can find this, we're done. And what's nice about this is that we know that this is linear, right? We know that this is linear, which means that, when y is equal to the maximum height, which is h, remember that our bounds of integration are going to be from y going from 0 to h. But when y is at the very maximum height, sigma at the top is going to be equal to little r, and sigma at the bottom is going to be equal to big R. And you basically just need to come up with a linear interpolation function to express sigma as a function of y any point in between.
Seems doable. I'm just not sure how to do it.
Right. It's how do I put it? It really seems really scary because all this is wrapped like this is like one of those Russian dolls, right? The outside is a calculus problem, but after like 2 or 3 layers in, you find out that this is actually a algebra 2 problem probably. And but because you've gone through all this like calculus context, you're kind of afraid, and maybe you think to yourself, oh, I don't know how to do this. But it hypothetically shouldn't be too bad, right? You can just define your coordinate system. Right? If you treat this as a coordinate system, and this is x, and this is y, we just want to find, how do we put it? We just want to find an expression for the line, right? We basically just want to figure out an expression for the line, and we know the line at 2 points. So this is literally like an 8th grade problem at this point. Where given 2 points, we need to find the equation of the line. And
you just find the slope?
Huh?
Just find the slope?
Yeah, exactly. You find the slope. You know what? I think I was making this a little bit more complicated than I need be. I probably shouldn't have called this sigma. I probably should have just called this x instead. You see why? I probably should have just called this x.
Okay.
To emphasize that at the end, we're basically just trying to find the equation of this line, which is going to be like y is equal to mx plus b, right? Y is equal to mx plus b, but then we want to isolate for x in terms of some function of y. So x and sigma are the exact same thing. I was just using slightly different notation, right? So I trust that you can find me y is equal to mx plus b, right?
Yeah.
Yeah. And once you have that, you solve for x as a function of y. You plug that into the integral, and then, my friend, you are done.
Oh.
Yeah, right? Not that crazy when you break it down into like step by step, is it? I hope every single step seems motivated.
I'm just wondering how you get area from
that. Just remind ourselves, right? I think we might have broken it down too much.
Oh, because it's squared pi.
Exactly, right? Really, we were looking too much at the 2D picture, but once we look back at the 3D picture, we realize that sigma, or x, is our radius at any given point. So the radius of the area of any of these circles is pi x squared. And then you multiply that by a little dy. And this becomes our differential volume, which is this thing down here. See how it's all kind of coming together, connecting together? Or like maybe this is like a Reese's cup integration. I don't know.
Don't really know how to put it into variables big R and little r though.
Big R and little r. Uh,
Yeah,
yeah, sure. Um,
because it's
I brushed
saying
over
put
that
it in
part.
terms of that.
Right,
Yeah,
I
I
know.
remember you said it was equal to like x was equal to like the top when it was on top it
Yeah,
was equal to little r and then at the
right.
bottom.
So I'm going to rephrase your question, right? And I think you're basically asking me, hey, we kind of solved the problem, and it didn't seem like little r or big R came into the steps anywhere. Where are they being used, right? That's kind of what you're asking. Yeah.
Yeah.
So remember, they came in. I kind of brushed over them, and I'm happy you asked because they come into play because you know at this point is r comma 0, and you know that this point is little r comma h, right? So r, little r, h, and big R are all going to be incorporated into your linear equation right here. You see that? Like all this information, like right now we're
So
talking about
those
kind
are
of information, but the fact that these two, like big R, little r, and h, define the points that, you know, the points of this line, that means that they're going to be involved in the expression for the equation of the line. And that means that after you isolate it, that means that you're going to have r,
h.
r, and h inside this expression for f of y.
Yeah. If if we're looking at the slope, I got h over little r minus big R.
Uh, yes, that's right. So I agree that slope should be h over r minus r. And
Then put
the
that
intercept will
in.
probably also have to depend on something like that too, right? You'll have to figure out what the
Well,
intercept is as well.
oh, you have to figure out the intercept as well.
Yeah, I mean, you need all the information for y is equal to mx plus b in order to isolate x, right?
But I have no what's it called? I don't have like I can't see where it passes through the y-axis.
I mean, you should be able to figure that out. Like I'm telling you from high school algebra, you should know that given any two unique points on the plane, um, like given their actual coordinates, you should be able to figure out the equation of the line, right?